will give you today a short presentation of some of the work that we have done so far on sealing material, elastomeric sealing material for hydrogen applications. So, as you may know, hydrogen is the smaller and lightest and most abundant in the universe, basically. It's not really available in the pure form, but mostly chemically bound in compounds, such as, for example, bound with oxygen in water or with carbon to have, for example, fossil fuels, hydrocarbons. For this reason, it can be considered more than an energy source, an energy vector or a carrier. It has, in principle, many advantages if we consider to use it as a fuel. We all know that this is a topic that is very much discussed lately. In principle, it would have no CO2 emissions if you produce it via the green hydrogen production route. It can be produced from renewable sources, which costs are still relatively high, but are supposed to be decreasing over the next years with new investments. It can be stored safely for a long time. It can be used for the so-called decarbonization of the heavy industry, such as steel industry, some heavy chemical, and so on. It can be used for e-mobility with the fuel cell technologies, and it can somewhat enhance the energy security by diversifying the fuel mix. Nowadays, there are, just simplifying a little bit, three main production routes for hydrogen. One is the very traditional one, so in the so-called gray hydrogen production route, where you start from reforming of hydrocarbons. This is a thermochemical conversion process that will lead to CO2 production equivalent to the hydrocarbon that are used to start the production itself. If you couple this technology with carbon capture and storage, you will then obtain a process that allow you to get decarbonized hydrogen, and in this case we will call it blue hydrogen production. The gray hydrogen production route is by far the most common one. It accounts for more than 95% of the production of hydrogen nowadays. We have then the, let's say, interesting one, or at least interesting for the future, which is the green hydrogen production route, which is still not very common, but it's the one coming from water and green electricity via electrolyzers. This is what can be kind of interesting for energy production in the future. As I said, there are still some technological gaps and some, let's say, research and scale-up topics to be handled for the green hydrogen production routes. Nowadays, let's say, if we look at the production method and the cost related to that, the gray hydrogen production is still by far the most convenient. But of course, new investments and new interest in this kind of energy will lead in the next years, most probably, things to change in this direction. So hydrogen can be used in different kind of markets and applications. It is for sure a source of heat, both for buildings, residential and commercial heat, as well as for the industry, like steel or heavy industry. Then, of course, it can be used as a fuel for transportation and to generate electricity. And on the other side, it's of course an important feedstock for many industries, such as refinery and the chemical industry. If we look at applications, the one that can be interesting for sealing or elastomeric sealing, which is what I'm going to talk about today, it's the use of hydrogen for transportation in general, especially for fuel cells and e-mobility. This can be applied to trucks, to passenger cars, to marine, to airplanes, and so on. Then, of course, there's the energy sector, where hydrogen can be used as a source of energy for some, let's say, heavy industry, but also for direct power generation and for the generation of, let's say, consumer energy. Then we have the pure production of hydrogen. As we mentioned before, production is being produced via different ways, for example, the green hydrogen production way, and then the use of hydrogen as raw material in the chemical industry, for example. So when we consider sealing in hydrogen application, we have to cope with very challenging requirements. On one side, we may have wide temperature ranges where the sealing should work. We have, for sure, usually requests about very high pressure that can go really high. We have to consider permeation. We have to consider, therefore, the compound compatibility with the hydrogen itself. And we have to consider the fact that we have very tight sealing requirements. So Angst+Pfister as a group is nowadays working to be prepared for these new kind of sealing applications, and we are working to validate our products or possibly new developments for these demanding environments. So that's what I'm going to describe you in the next few slides. Just before going into the, let's say, the description of what we have done and the results we have got so far, one important parameter to be considered when you talk about elastomers and gases in general, not only hydrogen, of course. Permeation is for sure a key property that you have to consider when you think about a gas in contact with a sealing, elastomeric sealing material. So the polymer structure can act as a barrier to the gas transport, but the gas can slowly diffuse through the polymer backbone anyway. So this process is characterized by two different thermodynamic properties. One is diffusivity, which describes the rate at which a species moves into the material, the polymeric material. And one is solubility, which describes or accounts of the quantity of permeant dissolved in the material itself. Permeation, the third property that we have to consider, is the product of these two, so diffusion and solubility. Permeation will depend on many different factors, temperature and pressure, first of all, at which we are working, thickness and surface area of the material in contact with the gas, polymer type, gas meaning monomer composition, which will lead to different free volume, chain mobility, polarity, degree of crystallinity, compound formulation, and gas type. Gas type meaning the molecule type and size, and the gas-material interaction that can be different depending on the elastomeric material and the gas we're talking about. Based on this, we did start our investigation to consider and to have an assessment on these parameters. We decided to start the investigation focusing on some specific elastomeric material, FKMs, EPDM, and HMBR. And we did start from 90-Shore compound. The choice was given by the fact that in most cases we did receive, let's say, requests from the market for hydrogen application that goes in the direction of very high pressure. Therefore, starting from hydrogen compounds was the choice that we decided to follow. What have we done? We have decided to collect some basic information about these different materials, doing some testing. So we carried out permeation testing according to ISO 27821, a leak test carried out according to an internal method, and rapid gas decompression testing according to the standard NORSOC M710, but in pure hydrogen. In all the cases, we did work at the same temperature and pressure conditions, 100 degrees C at 150 bar. For permeation, we did carry out permeation tests in pure hydrogen with 2 millimeter thick sheets. As for leak test, we did work with pure hydrogen and also a blend hydrogen 30% in methane on O-rings. And on the same kind of O-rings, we did run rapid gas decompression test in pure hydrogen as well. As I said, we did focus on HMBR, FKM, CPDM, and in particular we decided to work on 5 different materials, 2 HMBR, which have of course different monomer compositions and compound formulations. FKM, same story, so different kind of FKMs and formulations. EPDM, On all of them, we did permeation test and leak test, whereas we started to work on the rapid gas decompression testing with one of the FKMs, and we are planning to go on in that direction. But that's something I will also mention at the end of the presentation. So, on these slides, we summarize the permeation test results, 100 degrees C, 150 bar. As you can see, we have reported the permeation coefficient, which is the product of the diffusion coefficient and the solubility coefficient. Generally speaking, we can say that the permeation coefficient is relatively low, and this is due to the very low solubility coefficient. That's kind of interesting, because what we can observe from these results is that basically hydrogen permeation coefficient value are dictated by the diffusion due to the small molecular size of hydrogen. At the same time, so solubility is very low, so meaning that hydrogen is purely dissolved into these materials. This is different, for example, from CO2, where you may have very high diffusion, very high solubility, and this can cause, in many elastomers, potential rapid gas decompression issues. Generally speaking, so we can observe that hydrogen can move relatively fast into this material, so diffusion is fast, but only little remains absorbed into the materials themselves, so solubility is very low. As you can see, we have, let's say, reported the results from the best one to the worst one. So HNBR1 and FKM type 1 just resulted to be the best one, where the other was slightly worse. This was perfectly in agreement with the theoretical expectations. So permeation is influenced by the polymer type, that's for sure, and that's influenced by the compound formulation. So that was what we could confirm. At the same time, in parallel, we did run also some leak tests. Same conditions, as I said, temperature 100 degrees C, 150 bar, in pure hydrogen and in mixture hydrogen, methane, 30% hydrogen. And interestingly enough, we did find that the results here, or the ranking of the materials, is basically the same that we found with the permeation. This is suggesting that the main reason for gas passing through these materials is permeation or natural leakage. It's not then that the gas is going around the material or through discrete holes. So what is really dictating the leakage is natural leakage. So then, of course, if we compare pure hydrogen and hydrogen methane, we observe that we have more or less the same ranking, except for EPDM, which is, by the way, of course, behaving differently with methane due to their chemical affinity. But then, of course, the leak rate for the mixture with methane were just lower than in the case of pure hydrogen. This confirms basically that, yeah, hydrogen being a very small molecule, it's really, diffusing quite fast into these materials. So based on these results, permeation and leak tests that were quite well in agreement, and in agreement with some theoretical expectations as for the material, let's say, characteristics. We did start running some rapid gas decompression, pure hydrogen, according to the NORSOC standard, which is widely used in the oil and gas industry. And once again, we did it on FKM1. If you remember, it was one of the best performing materials, together with HNBR1. And basically, after the rapid gas decompression cycles at 100 degrees C, 150 bar, we got on all O-rings a very good rating, which is the best one, so 0000. So it looks like we didn't have any decompression issue with hydrogen in this case. This once again indicates or would suggest that possibly RGD or rapid gas decompression involving hydrogen should not be an issue for materials that are already proven to be RGD resistant to, for example, other gases, which are usually methane and CO2. All these materials that we have tested, so we have mentioned it before, were 90 Duro compounds that were tested and approved and proven to be RGD resistance according to the standard NORSOC testing or the NACE TM0297 in RGD testing in CO2 and so on. So we started from compounds that can be used for rapid gas decompression application in general. So, as said, it's probably due to the fact that we have very small quantities of hydrogen that remains dissolved into this material because solubility is very low, as if you remember the permeation results. And then we have a quick diffusion out of the material during the decompression. It looks like, there were no decompression issues with hydrogen. So as a conclusion, or more than a conclusion, I would say an observation, because this is still an ongoing work, we can say that permeation, so natural leakage, seems to be the main influence on the sealing function for hydrogen application, or the ones that we have investigated. Possibly RGD issue, no RGD issues with hydrogen can be present for proven RGD material resistance. And due to these, let's say, observations, we are going on with the work. As said, we are doing and planning more rapid gas decompression testing in pure hydrogen, going to pressures higher than 150 bar. We are also working in parallel on 70 Shorey solution for moderate pressure applications and validating therefore our let's say sealing materials, our compounds in hydrogen permeation and leakage. And okay, we are of course working together with our customers in different projects that involve sealing for different hydrogen applications. So thanks for your attention, and maybe there will be questions, I don't know. In any case, just want to say that we are in all 8, booth J76, so if you want to have some more information or go deeper into this topic, just come.